Section 11.4, video 2. If you made it to the end of the first video in this section, I mistakenly said that was the end of the section. I apologize. This is the second part of the section, although it's very short. And it's about estimating the sums themselves, not just whether they converge or diverge. So if we've already used a comparison test to show that our series converges or diverges, specifically converges, then we want to also know what's the sum or what's the remainder, just like we talked about in the last section. So remember that remainder is defined to be the true sum S minus your partial sum that you're using to estimate Sn. And it consists of all of the terms after that, an plus 1, an plus 2, and so on up to infinity. So for the comparison series Bn, whatever we're comparing to, we have to consider that remainder as well, which we call Tn, capital T sub n, which is little t, which is the sum of the series Bn, minus the partial sum that you use to estimate Bn. So since we're in the convergence situation, that an is less than or equal to Bn for all of our n, then we know our remainder for an is also less than or equal to the remainder for Tn. So if the series Bn is a p-series, we can estimate the remainder. If it's a geometric series, then it's the sum of a Tn, is the sum of a geometric series, and we can find the exact amount because we have a formula for that. Either way, we know that Rn is smaller than or equal to Tn. So an example, 1 over n cubed plus 1. Use the sum of the first 100 terms to approximate the sum and then figure out what the error is. So in this one, we know we're going to compare to the p-series 1 over n cubed. That's the p-series where p is 3. And we know that this series 1 over n cubed plus 1 is convergent using the comparison test because we can find a larger series, 1 over n cubed, that is convergent. Therefore, so is ours, 1 over n cubed plus 1. So what's the remainder? Well, the remainder for the comparison series, Tn, was estimated earlier using the remainder estimate for the integral test to be 1 over 2n squared. We did this in section 11.3. Therefore, the remainder for our series is also less than or equal to that value because it's less than or equal to Tn. So that gives us a bound, 1 over 2n squared. When n is 100, we have that our remainder, R100, would be less than or equal to 1 over 2n squared, which works out to be 0.00005. Now, if we use a calculator or a computer, and again, don't worry, I won't ask you to do this part, you can find that the sum of the first 100 terms, n equals 1 to 100, of 1 over n cubed plus 1 is about 0.686. And so we know from the top of the screen that the error on that estimate is less than or equal to 0.0005. In other words, the partial sum, the 100th partial sum, is a pretty excellent estimate for the sum of our series 1 over n cubed plus 1. And that is the end of section 11.4.